Alright guys, we have a few questions we need to answer this morning. Both are about Chapter 5. Chapter 5 is about anti-differentiation, and then area, and then definite integration. So here, let's first look at this one. This is the definite integral from -4 to +4 of t squared minus 3. Now we have covered all of Chapter 5, so you can notice, we just talked about this recently, that we have an even function. And we have an even function from -a to +a. If you really want to, you can actually say this is equal to 2 times the definite integral from 0 to 4 of t squared minus 3 dt. Now, why might that be more convenient? Because that 0 lower limit of integration just cuts down on some of the arithmetic errors possible. Especially because this means that capital F of 0, which is going to be part of the fundamental theorem of calculus, capital F of 0 is going to be 0, so again, just less room for error. But let's go ahead and just calculate this integral without using this fact here. Let's see what happens. So we know that to apply the fundamental theorem of calculus, we need to first find the antiderivative. So the antiderivative, we have a power rule, and then we have the antiderivative of a constant. So the power function here, the antiderivative, you simply increase the exponent by 1, and then divide by that new exponent. So the antiderivative of t squared is t cubed over 3. I should mention that we are kind of skipping the step that allows us to take the definite integral of a difference, and we're essentially breaking it apart into two definite integrals with the same limits of integration. But we typically skip that step because it's just so routine. It's in every problem. Anything that with multiple terms, not everyone, but a lot of them, we're going to immediately break it apart into two separate integrals and anti-differentiate both of them. So the first one is t cubed over 3, and then we have a constant, which to anti-differentiate the constant, we just add the variable of integration. I should say add. We multiply by a t. So there is the antiderivative. We call that capital F, t cubed over 3 minus 3t. And now we write this notation, -4 to +4, to indicate that we're about to apply the fundamental theorem of calculus. So this is capital F. We need to evaluate capital F at 4, and then subtract off capital F evaluated at -4. That's what the fundamental theorem, what we call the first fundamental theorem of calculus part, says to us. If you're out there on YouTube and you see this, some books call those the fundamental theorem, the first and the second. They swapped that labeling. Our book calls the way to evaluate this the first fundamental theorem of calculus. So let's see. Capital F evaluated at 4. So let's use lots of parentheses here. That would be 4 cubed over 3 minus 3 times 4. That's capital F evaluated at the upper limit of integration, minus, again, use lots of parentheses, capital F evaluated at -4 would be -4 cubed over 3 minus 3 times -4. Okay? So capital F evaluated at B minus capital F evaluated at A. Alright, equals, let's see, 4 cubed, 4 times 4 times 4, that's 64. So 64 over 3 minus 12 minus, don't lose track of your parentheses, -4 cubed, that is -64 over 3. Minus -12, so that would be plus 12. Okay, now let's see here. let's distribute this negative sign. So we'd have 64 over 3 minus 12 minus a negative, so plus 64 over 3 minus 12. Okay? So let's see what happens here. We have 64 over 3 minus 12 plus 64 over 3 minus 12 again. So let's see what this ends up being. To save a few seconds, I'll just go ahead and do this. Let's see, 64 divided by 3 times 2. And then that would be minus 24. We get 56 over 3. Now, I'm just curious, how much arithmetic would we cut down on by simply noticing this is an even function, as it's symmetric with respect to the y-axis, and we're integrating from negative a to a? How can we cut down on a little bit of arithmetic? Well, notice we're still anti-differentiating the same function. So we could say this is equal to, let's see, we have a 2 out front because we're going to double the integral from 0 to positive 4. So 2 times, all right, we have, let's see, t cubed over 3 minus 3t. And we are going to apply the fundamental calculus now, not from negative 4 to positive 4, but from 0 to positive 4. Okay? Now let's see here. Let's make that parenthesis a little bigger. So we're going to apply the fundamental theorem of calculus, get that answer, and multiply by 2. Now what's nice here is that capital F of 0 is going to be 0. So we have 2 times, let's use a bracket and then some parentheses, capital F evaluated at 4. That would be 4 cubed over 3 minus 3 times 4 minus capital F evaluated at 0, but that's 0 cubed over 3 minus 3 times 0. So notice we have 2. If we simplify here, we get 64 over 3 minus 12 minus 0 divided by 3, or 0 cubed divided by 3, 3 times 0, so that's just a big minus 0. And notice we have 2 times 64 over 3 minus 12. If we find that product, 64 divided by 3 minus 12 times 2, we get the exact same thing. 56 over 3. So I would argue that noticing this is an even function, therefore we integrated from 0 to 4, multiplied our solution by 2, that cut down on a little bit of arithmetic. So we didn't have to worry about distributing a negative sign and worrying about this part, because this part was 0. You get the exact same answer. Again, all we did was notice that this is an even function, that is, it's symmetric with respect to the y-axis. All right, now the other question we want to look at today is about finding the upper and lower sum estimates for a function. So we have y equals cosine x. Now the question asks us to use 4 rectangles. So n equals 4. And we want an upper and a lower sum. Now recall how we find upper and lower sums for a finite number of rectangles. Now we could go ahead and use the definition. We could say that the upper sum is going to be, use the formal sigma notation, where the sum from I equals 1 to 4 of f evaluate it at our c sub i's times our delta x sub i's, but probably don't want to do that here, because what's going to end up happening is we are going to have this situation. We're going to have the sum I equals 1 to 4 of cosine of, we'll have essentially, if we use the right-hand endpoints, we'll have cosine of, let's see, pi over 2 divided by 4, so pi over 8i, times pi over 8. That would give us, let's see, that's going to be the lower sum. Okay, using the right-hand endpoints here because it's a decreasing function, that would give us a lower sum. Here's the problem. We don't have, if you want to apply like the abstract definition of, then you convert this to n's and then plug in an n, like we've done for some of the quadratics and linears, like we do when we're doing a Riemann sum. We haven't memorized, or we have only memorized how to evaluate like the sum of the i's, the sum of the I squareds, and the sum of the I cubes. We don't really know how to abstractly deal with cosine of I. Now that is the definition, certainly. That is going to give us the lower sum, and I'll show you why that's true. But as far as doing this in an abstract manner, where we figure out how to simplify the sum of the i's, can't really do that here. But we'll come back to that in just a sec. Let's draw a picture. First of all, 4 rectangles. How do you find the width of all your rectangles? You take the interval and you divide by the number of rectangles. So essentially, delta x is always going to be equal to b minus a. We're going from 0 to pi over 2. So pi over 2 minus 0 over 4, because we have a finite number of rectangles here. So essentially, pi over 2 divided by 4, that's pi over 8. Okay? So pi over 8 is the width of each of our 4 rectangles. So let's go ahead and draw those. Let's see here, pi over 8, pi over 8, pi over 8. So let's label these points. If that's pi over 8, and then we go another pi over 8. Here, let me move this actually just a little bit to make them more evenly spaced out. If we go another pi over 8, well, pi over 8 plus pi over 8, that's 2 pi over 8. 2 pi over 8, also known as pi over 4. Add another pi over 8, and you have 3 pi over 8. Well, add another pi over 8, and you have 4 pi over 8, also known as pi over 2. So there are our 4 endpoints of our first rectangles, and then once that's for the upper sum, and then we'll use the right hand 4 up endpoints for the lower sum. Now, why do the left hand endpoints result in an upper sum, and the right hand endpoints result in lower sum? Well, just draw a picture. Okay, it's a decreasing function, so see what happens. Let's use the right hand endpoints. If I use the right hand endpoints of my interval, it means that I'm going to use the right hand side of this rectangle to determine the height. So I'm going to go up, 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 up until I hit my function, and that's going to be the height of my first rectangle. So here is my first rectangle. Its height is going to be determined right there. The height of my second rectangle is going to be determined by this point, pi over 8. I go up till I hit the curve, and then that is where I draw my second rectangle. And then I'm using pi over 4, 2 pi over 8. The right, did I say right? I can't talk today. I'm using the left-hand endpoint. If I said right, I apologize. I'm using the left-hand endpoints. Clearly, I don't know the difference between left and right today, apparently. I'm using the left-hand endpoints, And the left-hand endpoints, I see the left-hand side of every one of these rectangles. I go up vertically until I hit my curve, and then that is what determines the height of that rectangle. Okay, so there is an example of, or is the picture of the upper sum. Now, how do I describe this upper sum mathematically? Well, there's a few ways to do it. I could describe it in a manner similar to this. Now, I don't think it's necessary to do that, but sure you could. But notice that is not what I've described here with these rectangles. So let's see. I'll use sigma notation. It's the sum I equals 1 to n. Now, how do you find each of these heights? That's where the cosine of pi over 8 comes in. Now, it's not pi over 8i because that's not how we talk about left-hand endpoints. Left-hand endpoints are always given by the a, which in this case is 0. So 0 plus delta x pi over 8 times I minus 1. Now, why do we use I minus 1? Because I minus 1 times delta x generates a 0 first when you have to start your index at 1. We always want to start our index at 1, so that's why we have to use I minus 1 for the left-hand endpoints. So those are going to be all of the heights of my rectangles times the widths, which are pi over 8. So that's more like the abstract representation of what's going on here. Now, if you just want to write the concrete solution down, here's how you do it. Okay, how do you find the area of that first rectangle? Well, the area of the first rectangle is the height times the width. So we say, all right, let's do all the widths first. Every width is pi over 8. So pi over 8 times the height. What's the height? Well, the height is 1, but let's not write that down. The height is given by cosine of 0, that left-hand endpoint. That's the area of the first rectangle. Now the area of the second rectangle is, again, the width, pi over 8, times the height of that second rectangle. The height was given by cosine f of pi over 8. So cosine of pi over 8. That's the area of the second rectangle. Plus the width of the third rectangle. Every width is the same. Cosine, what's the next endpoint? It's 2 pi over 8, otherwise known as pi over 4. And the fourth rectangle, the width is pi over, oh, I said that's not right, pi over 8 times cosine. Now, what is the last endpoint? Left-hand endpoint is 3 pi over 8. Okay? If you wanted to be real fancy, you could factor out all the pi over 8s and then simply add up cosine of 0 plus cosine of pi over 8 plus cosine of pi over 4 plus cosine 3 pi over 8. And then get that answer and multiply by pi over 8. So let's just verify real quick with the calculator what is going on here. And I'm going to do just that. I'm going to factor out all the pi over 8s. So I'm going to factor out pi divided by 8. And then I'm going to multiply by cosine of 0. Well, cosine of 0 is certainly 1. Plus cosine of pi over 8. Plus cosine of pi over 4. Plus cosine of 3 pi divided by 8. And I get 1.1835. So this is an approximation for the upper sum. 1.1835. Okay? Now, what about the lower sum? Now, the lower sum, this is actually the abstract representation right here. Now, how do you draw the lower sum? This is when you use the left-hand endpoints. Excuse me, we just use the left-hand points. The right-hand endpoints. Because this function is decreasing, when we use the right-hand endpoints, we'll get a lower sum, and when we use the left-hand endpoints, we get an upper sum. So let's see here. If we use the left-hand side, that means I'm going to use pi over 8, 2 pi over 8, 3 pi over 8, and pi over 2 to give me the heights of my rectangles. Now, I kind of drew this to, not curved enough right here, so it's going to be kind of hard to tell for this first rectangle. I'm using the left-hand endpoint to determine the height. So there's the first one. Using the left-hand endpoint, pi over 4 now. And there's the second rectangle. Using the left-hand endpoint. And now what do you notice about when I use the endpoint pi over 2? Well, f of pi over 2 is 0. So there's essentially a rectangle here of width pi over 8. But when you use pi over 2 to determine its height, f of pi over 2, cosine of pi over 2 is 0. So there is a rectangle of height 0 there. There is no rectangle there. Okay? So the first rectangle is almost exactly the same according to my picture. Now, this graph isn't perfect. But then clearly you have a lower sum here. So we're going to add those rectangles. And again, the kind of the abstract version is the sum from I equals 1 to 4. Oh, there was supposed to be a 4 there. I said it in. I was getting ready to do a Riemann sum. Of cosine pi over 8i times pi over 8. All this says is add up heights times widths. That's all that says. Now let's see, let's do the same thing. Each of the widths is pi over 8, so pi over 8. So what's the height of this first rectangle? Okay, it's f cosine of pi over 8. Plus, okay, the width of every one of these rectangles is pi over 8. The height of this second rectangle is given by cosine of 2 pi over 8, otherwise known as cosine of pi over 4. Plus the third rectangle, cosine of pi over 8 times the height, which is cosine of 3 pi over 8. Plus the fourth rectangle, the width, again, the width is equal in every instance, pi over 8 times cosine of pi over 2. And if we add all of those up, again, we're going to be getting an approximation. Now, I should have said here, so the entire things here, the upper sum and lower sum are approximations inherently, but I should say this is an approximation to an approximation. This is the exact answer. If you want the exact answer to the upper sum, there's your exact answer. Now, I suppose you could say that's a 1, and you could figure out exactly what some of these are. Using, you would have to use a little bit of ingenuity to get that answer. That's not too hard. But we can get that answer off our unit circle, that answer off our unit circle, that answer using a half angle in our unit circle, and a little bit of ingenuity there. Okay? Same thing here. This is the exact lower sum. Again, the lower sum is an approximation, but we're going to get an approximation of the approximation by using our calculator, since that's what the homework dictates us to do. So let's see here. Again, I'm going to factor out all the pi over 8s, and then I'm going to simply add cosine of pi over 8 plus cosine of pi over 4 plus cosine of 3 pi divided by 8 plus cosine of pi over 2, which is 0. And I get 0.79 0.008 if we take it to 4 decimal places as the instructions indicate for us to do. Alright, so we have our essentially an approximation of an approximation, lower sum, upper sum. So what we know here is that the true area under the curve is somewhere between our upper estimate, 1.1835, and our lower estimate, 0.7908. True area. Now, why is this interpretation area? The interpretation is area because our function is non-negative over the interval 0 to pi over 2. Now, should we verify the result? If we verify the result, actually looking at the definite integral, we would say the definite integral from 0 to pi over 2 of cosine x dx, using the fundamental theorem of calculus, we would say this is equal to the antiderivative of cosine x dx. The antiderivative is sine x evaluated at our two endpoints, 0 and pi over 2. So what do we get here? Well, capital F evaluated at b, so sine, not sine x, sine of pi over 2 minus capital F evaluated at 0, sine of 0. So sine of pi over 2, sine of pi over 2 is what? Well, think about your unit circle. Sine of pi over 2 is 1. Sine is 0. So there is the true area under the curve. So the true area is 1, which certainly is in between these two estimates. So this is where we started way back in section 5.2, and this is where, kind of close to where we ended in section 5.4 is where the fundamental theorem of calculus happened. So estimates is where we started, finding the area via estimates, upper and lower sums. And now we can find the exact integral, in this case the exact area under the curve, by evaluating the definite integral. Alright, I think that's about all I have time for. I have class in 4 minutes, so I hope this has been helpful. If you have any more questions, always feel free to ask. See you soon.